Good afternoon. It's my privilege to be here again for my course, Engineering Thermodynamics. Today, I am going to discuss about some numericals on Otto cycle. As of now, we have covered the Otto cycle, diesel cycle, dual cycle, and their efficiency, their performance, their state points, work done, heat rejected, heat supplied. All these things we have done mathematically as well as theoretically. In today's lecture, I am going to discuss about numericals related to the Otto cycle as well as diesel cycle. So here it is not only Otto, it is also diesel. So this I will be discussing here in this lecture. So here there are 4 numericals in this, and out of that 3 are from Otto cycle and last one is from the diesel cycle. So these 4 numericals we are going to discuss. So numerical problem 1 on Otto cycle. I will read out this problem and then we will proceed ahead. An internal combustion engine with compression ratio of 6 and the pressure and the temperature at the beginning of the compression are 1 bar and the 30 degrees Celsius. The peak pressure is 40 bar. Find pressure and temperature at all points, efficiency and the mean effective pressure. So what we have to find out? So in this problem, an IC engine with compression ratio. So compression ratio, and what is the compression ratio? We are normally write RC, and RC is equal to V1 by V2. So if I take a plot of PV diagram, P and V, and if this is the Otto cycle, so this is the 1, this is the 2, constant volume heat addition, and then like this. Okay, so this is the process. So in this is the V1. So 1, 2, 3 and 4. So this is the V1 is equal to V4, and this is the V2 is equal to V3. So compression ratio V1 by V2 is given 6. This is given here 6. And the pressure and the temperature at the beginning of the compressor. So this is the beginning. So T1 pressure is 1 bar, that is atmospheric pressure, and T1 is 30 degrees centigrade. These things are given. All the temperatures we have to make it in the Kelvin. So you have to add 273. So 303 Kelvin. Always we have to. So we have to, the peak pressure is given. So this is the peak pressure, P3. So P3 is given 40 bar. So these parameters are given. What we have to find out? First, pressure and the temperature, P and T at all points. All points, it means P1, T1 is given, P2, T2, P3, T3, P4, T4. These things we have to find out. Second thing, efficiency. Efficiency of the cycle, that we have to find out. And third one is the mean effective pressure. Mean effective pressure. This we have to find out in this problem. So let's see how we can go ahead. So first we have to understand the problem, that starting point 1 and 2. This starting point 1, pressure P1 and the T1 is given, and at the highest pressure P3 is also given as a 40 bar. So these 3 things are, and also the compression ratio means V1 by V2 or V4 by V3 is equal to 6. These things are also given. So let's see and start the process. So first we have to draw the PV diagram. In PV diagram 1, 2, 3 and 4. So P3 is given 40 bar. Here P1 is equal to 1 bar and T1 is equal to 303 Kelvin. These things are given and the ratio V1 by V2. So V1 by V2 is equal to 6. These parameters are given. So we have to find out one by one and how to proceed. So given P1 is equal to 1 bar, T1 is equal to 30 degrees centigrade plus 273, 303 Kelvin, R is equal to 6, P3 is equal to 40 bar. These all things I have shown in this PV diagram. So here process 1 and 2 is a isentropic process, isentropic compression. This is given. This 1, 2 is so T2 by T1. So at this point, temperature at this point divided by temperature at this point, T2 by T1 is equal to V1 by V2 gamma minus 1. We know V1 by V2 is a compression ratio and it is a 6. So here T1 is equal to 303, V1 by V2 is equal to 6, 1.4 minus 1. So if you calculate, you will get the temperature at the point 2 is equal to 620.44 Kelvin. So this is the first point of point 2. We got one parameter. Now we have to find out the T2 in this. The pressure of this we have to find out. So now to find the P2. So this P2 is again we have to find out the relation with adiabatic compression 1 to 2. So we know that P2 by P1 is equal to V1 by V2 to the power gamma. So V1 by V2 is a 6 and gamma is equal to 1.4. So P2 you will get P1 is equal to 1 bar into 6 into 1.4, 6 to power 1.4, you will get 12.29 bar. So the pressure at the point 2, we got P2 is equal to 12.29 bar. So this is the another answer. So we got here P2 and the T2. Both we have achieved. Now our objective is to get here P3 is given. So what is the T3? That we have to find out. Then here we have to find out T4 and P4. This all if we are able to find out, our problem is will become very easy. So now to find the temperature T3, we know the P3 is given 40 bar from the process 2 and 3. So 2, 3 is a constant volume or isochoric process. We can use the gas equation P1 V1 by T1 is equal to P2 V2 by T2. So P1 or P3 by T3 is equal to T2 by P3 by P2, P3 by P2. It is not. So P3 by T3 is equal to P2 by T3, T2 by T3. So T3 is equal to P3 by P2, P3 by P2. So T3 is equal to P3 by P2 into T2. Okay, so here this is P3 by P2. P3 by P2 is equal to T3 by T2. So here you will get T3 is equal to P3 by P2 into T2. Okay, so here P3 is given 40, P2 is given this, and this we have got the T2 from here. T2. So we can get here that T3 is equal to 2019.33 Kelvin. So here we got 2019.33 Kelvin. Okay, so this we can see here that P3 by T3 is equal to P2 by T2. P2 by T2. So T3 is equal to P3 by P2 into T2. Okay, so Just you have to see this one. Okay. So here we got the temperature T3 and T3 is equal to 2019.33. So in this we can see that at this point, at point 3, your pressure is very high and temperature is also very high. Now we have to see the next, how to find out the T4 and the P4. So we will go ahead to find the P4 and the T4. So we know that T4 for adiabatic process 3 and 4, T4 by T3 is equal to V3 by V4 to the power gamma minus 1. So T4 is equal to T3, V3 by V4 gamma minus 1, and V3 by V4 is equal to 1 by R. So here we will get T3 1 by R to the power gamma minus 1. So T3 is equal to 2019.33 divided by 6 to the power 1.4 minus 1. So here you will get the temperature at the 4, you will get 302.99 Kelvin. 302.99 Kelvin. So in fact, this is the same temperature what we have started, that is 303. Means T1 and the T4 are almost same. So to find the P4, so P4 by P3 is equal to V3 by V4. So P4 is equal to P3 into V3 by V4 to the power gamma. So here we will get P3 1 by V4 by V3 to the power gamma. So here you will get P3 by R to the power gamma. So here P4 is equal to 40 divided by 6, 1.6 to the power 1.4. It is 3.256 bar. So at the T4 you have 302.99. You can write as a 303 as a T1, and the P4 is equal to 3.256 bar. This pressure is higher than the P1. P4 is greater than P1, but T4 is less than T1. This we have got. So now to find the efficiency of the cycle. How to find the efficiency of the cycle? So we know that the efficiency of the cycle, directly equations we can put it here for the Otto cycle. So to find the efficiency, eta is equal to 1 minus 1 by R to the power gamma minus 1. R is given 6. Gamma is equal to 1.4. If you put this value, you will get 0.5116 or 15.16%. So the efficiency of this given system is 51.16%. It means we are supplying the amount of heat out of 100, only 51.1% is only utilized. Remaining nearly 49 or 48.84 is going as a waste. That much energy we are wasting. So how we can improve? That is the area of the research where we can apply our brain and we can find out that how we can get the better efficiency. That is the objective of our studying or any research work, to how to find out. So we got now two things. One is all the temperature and the pressure for each point. Second, we have got the efficiency. This is the second point. And now we have to find the third point, that is the mean effective pressure. So what is the mean effective pressure? That we have to see first. So if you see here, this is a PV diagram of Otto cycle. So it is like this: 1, 2, 3 and 4. So if you see, here is a P1, this is the P2, this is the P3 and this is the P4. So which pressure we have to take? So we have to take a mean pressure. So that mean pressure which gives the work done, that average pressure of this total cycle, if you add in the system, that pressure into work is equal to PdV, means that pressure, average pressure of the whole system, that will give the mean effective pressure. So we know that Qin is equal to CV T3 minus T2. So CV is equal to 0.716. T3 we have find out 2019.33 minus 620.44. So you will get 1001.61 kilojoule per kg. But we know that this eta is equal to W by QH. So W is equal to eta into QH. So here we know this eta, we have got 0.5166 into QH, we got 101.61. So we got the work done is equal to 520.42 kilojoule per kg. But we know that work done is equal to P mean effective pressure into dV. So PMEP into V1 minus V2. So mean effective pressure is equal to work done, net work done divided by V1 minus V2. But we don't know how much is V1. So by using the gas equation, P1 V1 is equal to RT1. So this V1 is equal to RT1 divided by P1. R is 0.287 into T1 is 303 divided by P1. This we have to put the kilopascal. You have to very much take care. It is 1 bar. 1 bar is equal to 100 kPa. So V1 we have got 0.8696 meter cube per kg. So from this V1 we can find out the V2. So V2 is equal to 0.8696 divided by 6. So you will get the. So now you can put here that net work done which we have got 520.42 divided by 0.8696, 1 minus 1 by 6. So you will get here 7.07. Here we got the kilopascal and divided by 100, you will get 7.07 bar. Okay, so here we got this 7.07 kilopascal. So kilopascal to divided by 100, so you will get the bar. So mean effective pressure is 7.07 bar. So this is our final answer which we have got. So I think by this numerical we are able to understand that how to find out the state position if we know the initial point and somewhere in between the maximum temperature or the maximum pressure or heat supplied. If you know the heat supplied, from there also QH is equal to CV T3 minus T2. From there also we can find out the T3. So if heat supplied is given, maximum pressure is given or maximum temperature is given and the initial conditions are given, we can very well find out the whole system by using the thermodynamic relations. So in this way we can find out this all the answers. Now I will go for the next problem about another problem for Otto cycle. So in this, just I am just reading out. To approximate an actual spark ignition engine. Here it is a spark ignition engine means Otto cycle. Okay, because Otto cycle are the constant volume cycle and spark ignition is only given in the petrol engine and these petrol engines are the spark ignition engine. Consider an air standard Otto cycle that has a heat addition of 1800 kilojoule per kg. Means Q in is given of air, a compression ratio RC is also given and a pressure and the temperature at the beginning of the compression process of 90 kilopascal and 10 degrees centigrade. Assuming constant specific heats, determine the maximum pressure and the temperature of the cycle and thermal efficiency of the cycle and the mean effective pressure. So we have to find out, determine the maximum pressure and the temperature of the cycle and the thermal efficiency. So What is the maximum pressure and the temperature? I think you all know. So if this is the 1, 1 to 2, 2 to 3. So this is the P and this is the V. So 1 to 2 and this is the 3. So P3 and the T3 will give the maximum P and T. So we have to find out P3 and the T3. P1 RP is given, that is compression ratio. RC is given 7, that is V1 by V2 is given. So this V1 by V2 is given as a 7 here, 7. V1 by V2 is given 7 and heat added. So this heat Q in is given 1800 kilojoule per kg. So these things are given and we have to find out the maximum pressure and the temperature. Then so maximum P and T, that is P3 and T3 we have to find out. Second, we have to find out the eta, thermal efficiency, and third we have to find out mean effective pressure. So like the previous one, in that temperature was given only pressure, P3 was given, here P3 and T3 not given. But in place of P3 and T3, how much heat is added in the constant volume process? That is 1800 kilojoule per kg is mentioned. So here, this is the your petrol engine or the spark ignition engine. So this you can see here that this is the inlet and this is the exhaust. So here is the piston. This piston is moving up and down. So initially it is here at the top dead center. As it is moving down, this valve is opened and the air and the fuel mixture, air plus fuel mixture is entering. And this air and fuel mixture, when it reaches to the bottom dead center, both the valve, that is inlet valve and the exhaust valve, both are closed. Now both are closed and it is started moving up like this. So this much volume which is from here to here, this much is again it is reduced to only this much here. Very compressed air fuel mixture is here. As it is reaching here, then spark is giving the electric spark and this fuel is burnt. So just I am drawing here again this same process. So here it is PV diagram. This is the suction, then this is the compression, this is the ignition, this is the expansion, like okay, like this. So initially when it is down, it is moving like this, and after that it is going out. So this is the compression, 0, 1, 2, 3 and 4. So it is a compression. So compression is from 1 to 2, compression is done, 2 to 3, heat is added here, Q in is here. So this is given, this is the first condition is also given, 90 kPa and 10 degrees centigrade. So the P1 and T1 and this heat is given. These are the things are given. We have to find out P maximum means P3 and T3 and efficiency we have to find out and mean effective pressure we have to find out. So this is the problem and I think it is now understood that how to solve and all as we have seen in earlier also. So let's see and we will see how to do this problem. So here it is a PV diagram and the TS diagram. So here 1 to 2 is your isentropic process, isentropic compression. 2 to 3 is heat addition at a constant volume. This is the your expansion process, isentropic. 3 to 4 isentropic expansion and this is the heat rejection. 4 to 1 is heat. This is also isentropic. Okay, so we will see it how it is working. Now one PV diagram, and now we will see the TS diagram. So this is your state 1. If you compress it, pressure and temperature will increase from T1 to T2. From here, T2 we will add the heat. Lot of temperature will increase again here. P2 to P3, T2 to T3. Pressure and temperature is increased. So you reach here at the point 3. Now it is expanded. So here S is equal to constant, and here is S is equal to constant. This is V is equal to constant, and here also V is equal to constant. This is isochoric. So in this Otto cycle, we have the 2 isochoric process and 2 adiabatic, reversible adiabatic or isentropic processes. And here the given is QH is Q23 is equal to 1800 kilojoule per kg. Compression ratio is 7. Pressure at the point 1 is 90 kilopascal. Temperature T1 is equal to 10 degrees centigrade plus 273, 283 Kelvin, and gamma is, if not also given, you have to consider 1.4. This has to be remembered. So now we have to find out the state location from 2, 3, 4. All the points we have to find out. First we have to start with the process 1, 2. This process 1, 2 is a adiabatic or isentropic process. So we have to use the adiabatic relations. P1 V1 to the power gamma is equal to P2 V to the power gamma. So P2 by P1 is equal to V1 by V to the power gamma, and V1 by V2 is given 7 and gamma is equal to 1.4. So we got here P2 is equal to P1 into 7 to the power 1.4, and the P1 is 90, so 90 into 7 to the power 1.4. So we got here, this you can calculate the further. I have not here the given exactly how much P2 we have got. It is for you to make the calculation and find out the answer. Now for the ideal gas, if we write for the P1 V1 by T1 is equal to P2 V2 by T2. So we can write that T2 by T1 is equal to P2 by P1 into V2 by V1. So this T2 is equal to T1 P2 by P1 into 1 by R. So here T1 is equal to 283, and this P2 by P1 is equal to 7, 1.4 divided by 1 by 7. So here you will get T2 is equal to 616.6 Kelvin. Okay, so here pressure ratio and the compression ratio, it is mentioned as the same. Okay, so this we have to see it. So now how to find the T3? Using QH is given, that is the heat added. Heat added is given. So 1800. So this QH is equal to CV T3 minus T2. So 1800 0.717 T3 minus 616.6. So T3 is equal to 1800 divided by 0.716 plus 616.6. So we will get 3127 Kelvin. Or if you can reduce minus 273, you will get the in degree centigrade. So T3 we got 3127 Kelvin. So this is the highest temperature. Highest temperature or maximum temperature. Okay, so we got here the maximum temperature. So what is the maximum pressure? P3 is equal to P3 by P2 is equal to T3 by T2. So T3 we know 3127 and T2 also we know. So we can get the P3 is equal to 3127 by 1800 into 90 into 7 1.4. So we will get something P3 also here. Answer you have to find out. Please calculate. Please calculate it. Okay, so you will get this all the parameters. So now we have to find the efficiency of the system. So total to find the efficiency, we know that eta Otto cycle is equal to 1 minus QL by QH. So this we can write 1 minus CV T4 minus T1 by CV T3 minus T1. CV is cancelled, and we will take the T1 here constant. So 1 minus T1 by T2, T4 by T1 minus 1, and T3 minus T2 minus 1. These things are same. So here we got 1 minus T1 by T2. So 1 minus T1 is equal to 283 divided by T1 616.6. So you will get 0.541. So this eta is equal to 54.1%. So we got this efficiency of the cycle as 54.1%. So now we have to see the work done. So this work done is equal to PDV, and this is equal to W net. Efficiency is equal to W net by QH. So W net is equal to efficiency into QH. Efficiency is 0.541 and QH is 1800, and this is equal to MEP into V1 minus V2. But how to find out the V1? We know the ideal gas equation, P1 V1 is equal to RT1. So V1 is equal to RT1 by P1. So from here we will get the V1, and this is the MEP is equal to 0.541, this one, divided by V1 minus V2. So 0.541 into 1800 divided by V1 minus V1 by R. So here 0.54 into 1800 divided by V1 1 minus 1 by R. So mean effective pressure we will get 1258 kilopascal or 12 bar. This is the mean effective pressure of this system. So we can, I am ending here, and we will see for the next, I am again taking the next 2 more numerical for the next lecture. Okay, thank you very much for the joining, and please be tuned for my next lecture, and I will be taking one this diesel cycle, and another I will be taking this Otto cycle again. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.